So let's write that out for a few examples. For n equals to 1, so we would have the coefficient of the kth basis state, which is the kth 0th order state, to the first order wave function. So if n is equal 1, that sum disappears because it goes to n minus 1, so we don't have this one, we only have this here. So we get a sum over j, k, h prime, j divided by the difference of the 0th order energies. But then let's look at this one. So what would we have? We have n equals to 1, which is j 0 then. But j 0th order, we talked about already before, that the only one, that is the coefficient of the j's state in the 0th order wave function. But the 0th order wave function consists only of 0. So from this sum over j, the only term which survives is the one where j is equal to 0. And that coefficient, being that the only one in that state, in that wave function, is 1. So this is delta j 0. So only if j is equal to 0, it gives something. Well, that doesn't belong to that equation, sorry. And that means we just get a single term. We get the term where j is equal to the 0th unperturbed state, which sort of removes the thing which always irritates me when I write that up, that I have 0 down there and j is still here. But now we have 0 and 0 and k and k. I always have to look, is that correct? So that's a very simple coefficient. You need two of the unperturbed states. It's the matrix element of the perturbation between two of the unperturbed states. Your reference state, our expansion for the whole expansion point, and then the state whose coefficient we look at, and is divided by the energy difference. Divided and therefore also weighted by the energy difference. That means the higher the energy of this kth basis state is relative to the state we're looking at, the less important that coefficient is going to be. Sort of weighted by the energy difference. How high is up? And you also can see that this kind of perturbation theory runs into a problem if your 0th order state, this one, your 0th order reference state is degenerate. If it's degenerate, this and k is then the other degenerate state, you have a problem and you can't use it. So this is actually non-degenerate perturbation theory. If you have a reference state, the unperturbed state which you want to correct because of the perturbation, and that state is degenerate, you have to use a different kind of perturbation theory. There's degenerate perturbation theory where you can handle that problem, but this is for non-degenerate states. The second order coefficient, k second order, that unfortunately we have to take the whole thing. We also get a contribution from this sum now, so that's not going to look so nice any longer, or simple. So we get a sum over j, And I actually now remove that 0 immediately, because I know that that's not going to be there. We had that before. And then I get a k, h prime j divided by E0 minus ek. And now it's times the corresponding first order coefficient, j, and n is now 2, so I get a first order coefficient here. Minus, and from here I get a first order energy, and I get c epsilon coefficient c, k first order divided by the same denominator. And then of course I can insert my 2 first order coefficients. Which then makes this sum over j not equals to 0, k, h prime, j, h prime 0, that's this one, divided by E0 minus ek, now in parentheses because I have to multiply it with that one, which is E0 minus ej. And then my first order energy, which just looks like this, because the Hamiltonian is first order, so I just have 0th order wave functions, and then I get the same coefficient again. I get, now I really get k, h prime 0, and I get E0 minus ek squared. I have it once here and once there, so I get it squared. So that's a bit more complicated expression. So you really have a sum over all, in a way, intermediate states over all the other states.